Okay, so Sophie, here are those remaining problems. So for the first one here, polynomial function with the rule f of x, the derivative satisfies blah, blah, blah. And that means basically it's got stationary points at A and B. Here's A, and here's B. All right, now f dash x, so the gradient is more than 0 between A and B. So I'm just going to draw something that would satisfy that. The gradient is less than 0 when A is less than 0. So it's got a negative gradient when A is less than 0. It's got a negative gradient for values of x less than A. So let's draw that. So negative gradient for values less than A. And it's got a positive gradient for values of x greater than B. So the graph stays positive. So we've got 0 gradient, 0 gradient, and the rest of the gradients satisfy the kind of requirements. All right, so now what we've got is a local min at A and an inflection at B. So let's see. Local minimum at A comma f of A and stationary point of inflection. Yep, that's our answer, E. All right, the graph of a polynomial function with a rule has a local maximum at the point with the coordinates A, f of A, local min at the origin, but no other stationary points. All right, so let's have a look at it. So it's got a local minimum at the origin and no other stationary points. So where's its minimum at the origin, local maximum at A, f of A. Right, so there's our function. All right, now the graph of the rule where k is okay is, right, so what we're going to do is basically do this transformation here. So what I'm going to do is redraw my transform function. So let's take this point here, which is 0, 0, and transform it. So what we need to know is that this thing here is a reflection in the x-axis, i.e. does nothing. Dilated factor 2 from the x-axis, i.e. does nothing. Dilated factor of 2 from y does nothing and goes up k. So that is going to be my point there. Now, what about this one here, A, f of A? So let's say that this one here, that's its original point. What we're going to do is run the transformation. So it gets reflected in the x-axis, so it's down to here, dilated by a factor of 2 from x, so it's doubled, it's like way down here, all right? Then dilated by a factor of 2 from y, so it goes over to here, and then it goes up k units. Okay, so it's going to be like way out here. I'm going to draw it not to scale, but essentially what's going to happen is it's going to go like this now. All right. Now, what is our answer? So this one here is going to become a local maximum. All right, so our local maximum, coordinate points. So none of them are the correct. So each of them is going to be like based on slamming in. So it's always going to be based around this one. So our coordinate is, it's going to be a minimum. It's going to be either B or E. All right, now what's our coordinate? So it's going to be, this thing here is a dilation factor 2 from the y-axis. So our A value is going to become 2A after it's being dilated by a factor of 2. So actually the answer has to be E. It's got to be E, okay? So the X value will become this, and our Y value when it's banged in will be that based on this. Actually, it will be, because if I put 2A into this, I'm going to get a negative 2 f of 2A on 2 plus K, which is going to be negative 2 f of, that cancels out, f of A plus K. Yeah, definitely E. All right, that's a hard question, that one. I reckon it's difficult. All right, the last question is this thing here. All right, so I think what we got, or what you might have got up to, is C. Right, I'm just going to try and get a bit more space on this one so that I can do it and start drawing some pictures, because I think that's going to be an important aspect. In fact, no, I'm going to draw a lot of these pictures on GeoGebra, but yeah, you could equally do a lot of these pictures um, on the CAS or on a piece of paper. All right, so what I had to do was solve the derivative first of all. So I got a derivative of f dash x equals x take beta, n take 1, x take alpha, m take 1, all multiplied by m plus n x take away alpha m take away beta n. Open, open, close, close. All right, and then what we do is we solve it for 0. So 0 equals this. I'm not going to rewrite it all, okay, but we let f dash x equals 0, which means that we're going to get beta. So x could be beta, x could be alpha. And let's solve this one here. 0 equals m plus n x take away alpha m take away beta n. All right, so I'm going to add this to both sides. So I'm left with alpha m plus beta n equals x, and m plus n. We're going to divide by m plus n, so x is equal to alpha m plus beta n all over m plus n. Right, so there's our three solutions. So we've got a solution there, a solution there, and a solution there. I.e., what they're basically saying is I've got 0 gradient at those points. All right, so let me just pause this. Okay, so now what I'm going to do is set up a few scenarios. Okay, so I'm going to say here in this part D, part 1, if m and n are odd, find the values for which f dash x is greater than 0, i.e. when it's going to have a positive gradient. So let's set up a possible scenario. Let's make n equal to, what's the rules here? M is larger than n. So let's make m 3 and n 1. Okay? All right, so here's how it's going to work for that. So we're going to get alpha and beta as solutions. What's going to happen is, so this is going to be a power 1 by a power 3, which is going to be, we're going to get a power 4 function. This is going to be x to the 4, okay? Now, the important thing to know about that is that a power 4 function will behave like a quartic, which will behave like a parabola, i.e. it's going to start with a negative gradient. So what's going to happen is the negative gradient will come down, swing through that solution there, and what it needs to do is swing back up and go through this point here. And because this is a power 3 solution, that means it's going to inflect at that point. So that's what my graph is going to look like with n equal 1 and m equal 3. Two odd numbers where m is larger than n. All right. Well, then we can see here that what we've got is when we're going to have a positive gradient, when is f dash x going to be larger than 0? Well, it's actually going to be from here onwards, not including beta, because it's got a 0 gradient. Now, what is this stationary point here? Well, actually, that's this one here that we just worked out earlier. So my suggestion is that it's going to be all the values of x larger than this value here, not including beta. Okay, but let's draw another version of this graph. So I'm going to chop around a little bit here and go, all right, this is alpha and this is beta again. And what I'm going to do is make x take alpha 3 and x take beta 5. All right, so what's going to happen is we're going to get here, if I expanded this out, I'm going to get an x to the 3 by an x to the 5, which is going to give me an x to the 8. So that's an even number. Okay, so note that that's going to behave like a quartic, which is going to behave like a parabola. It's going to start with a negative gradient. What's going to happen is this is going to be an inflection point. It's a power 3 solution. It's going to turn back up, and it's also going to be an inflection on that because that's a power 5 or an odd solution is the way I think about it. Okay, and again, what you'll note here is that it's going to have a positive gradient from this stationary point onwards, not including B. And this is going to happen, this same shape is going to happen for a 5 and a 7 and a 9, for all of them. So my suggestion is that for part D, we're going to get a solution of alpha m plus beta n all over m plus n. That's the stationary point or the x value. That's going to be this stationary point. It's going to be this stationary point all the way up to infinity. But hey, I just need to remove beta from that because that, whoops, not a curve. I need to remove beta from that because that is always going to be an inflection point or a stationary point of inflection, and that's going to be a 0 gradient point, not a positive gradient, a 0 gradient point. But the gradient is going to be negative everywhere else, 0 gradient there if you want to get technical. All right, so that's my answer to part 1. All right, now I'm going to clear out some of this chaff and answer part 2. All right, now if m is odd and n is even, all right, so let's draw up a potential problem for that. So x take alpha, x take beta, where m is odd. So let's give it a, what's the rules? M has to be larger than n. So n has to be even and it's positive. So that's the lowest value that can be is 2. And that means that m has to be larger and it has to be odd. So we're going to make that one 3. All right, what would this graph look like? So we're going to get this situation. That's alpha, that's beta. All right, so this is a power 2 solution. This is a power 3 solution. So that's going to be a bounce. That's going to be an inflection. All right, what kind of function have I got? Well, this is going to be an x to the 2. This is going to be an x to the 3. They're going to get multiplied together to be an x to the 5. Now that is like a cubic function. That's like an x to the 3. When you know that when we've got cubic functions and positive cubics, they start with a positive gradient. So what is going to happen here is I'm going to come through here, bounce, come back down, come back up and inflect there. Okay, so I'm going to come up, bounce, and I need to inflect here, which means I need to turn. Now, what's the turning point? Well, it will be the same turning point we discussed before, and I've got it written down on a piece of paper next to me. It's going to be negative m, negative, why do I keep saying negative? Alpha m plus beta n all over m plus n. That's the stationary point there. Okay, it has to be that stationary point. So, what I'm suspecting is that all cases will be like this. So we've got a positive gradient here, and we're going to get a positive gradient from here, not including this beta value. Okay, so I'm going to suggest here that the answer to part B is going to be negative infinity all the way up to alpha, not including it because that's a 0 gradient point, union with, same answer as before, alpha m plus beta n all over m plus n to infinity, but we've got to exclude, so I'm just really compressing this in, so my apologies there, Sophie. We've got to exclude from that beta itself because that is a 0 gradient point. So my apologies there, that's a squiggly bracket, beta, close squiggly bracket, because we've got to include that. Now, how do I know this is the case? Well, what I'm going to do is change this to the next even number, which is 4, and this goes to an odd number, which is 5, okay? So what would that graph look like? Well, again, that's quartic behavior. That's going to be parabolic behavior, which is going to be bounce. This is going to be inflection behavior. That's power 5. That's inflection behavior. So at alpha and beta, we're going to get those. Now that's going to be an x to the 4 multiplied by an x to the 5, which is an x to the 9, which behaves like an x to the 5, which behaves like an x to the 3, which means we've got to start an x to the 9 with a positive gradient. So it's going to come up, bounce, turn back, and whoop, I was going to try and inflect there, inflect, i.e. it's going to be exactly the same as this. So I have no doubt that this is going to be when x is got a positive gradient. X is an element of those solutions, negative infinity all the way up to my alpha value, union with m plus, so alpha m plus beta n over m plus n, all the way up to positive infinity, but chop out beta because we momentarily are zero there.